Hello, in this video, we're going to look at Green's theorem. Okay, so to get started with Green's theorem, first we need a vector field. And we'll say it's a pi plus qj, and it defines a vector at every point in R2. Suppose that we also have a closed curve C. And we'll say that's defined by x equals x of t, y equals y of t. And if you combine them, you could define vector function r of t from t being defined from a to b. And C is oriented counterclockwise. Around region D. All right, so if we were to draw ourselves a picture, so we're dealing with 2 dimensions here, 2 dimensions, not 3. Green's theorem is for 2 dimensions. So the idea is we've got some curve. There's C. It's got orientation counterclockwise. It surrounds region D. And then at every point in this picture, we have a vector from our vector field. All right, so there are 2 formats for Green's theorem. Green's theorem says that if you go through and calculate f dot dr over curve C, then that equals the curl of f dot k dA over d. And the alternate form is p dx plus q dy equals the partial of q with respect to x minus the partial of p with respect to y dA. Okay, so you can use either one of these 2 formats. They're the same. If you take f and plug it in here and here, you can actually simplify from the top form to the bottom form. Okay, so before we get into the why does this work? Why is Green's theorem true? The first thing that we're going to do is we're going to talk about these 2 left-hand side things. So frequently what you'll see, so you notice this is the work integral format. This is not usually interpreted as a work integral. Instead, it has a different name. So frequently you'll see like a little circle here that's put around the integral symbol with a counterclockwise arrow. So what these things are called on the left-hand side, they're called circulation integrals. So why would they be called a circulation integral? So let's think about that. All right, so this is called a circulation integral. All right, so the reason is that if you think about what f and dr, you think about this calculation, right? Actually, let's actually go out to the side, right? So if you've got 2 vectors, vector A and vector B, and they are pointing in the same direction versus vector A and vector B pointing orthogonal to each other, like what do we know about the dot product between these? You have A and B is going to be very large when they point in the same direction, and A dot B equals 0 when they are orthogonal. Okay, so if they point in opposite directions, the dot product gives us 0. If they point in this, if they're parallel, if they point in the same direction, then you get a very large value. All right, so if we think about this integral here, if we think actually about doing the calculations, if we think about actually dot producting f and dr, then this integral is going to have a large value when f and dr are in the same direction. Okay, and the reason is what we just said. All right, so this is a dot product calculation right there. And so you're going to get a large amount here when f and dr are in the same direction, and you're going to get 0 when they're orthogonal. All right, and so the question is, what is dr? So since dr points in the direction of the tangent vector for the curve, right? So since dr points in the direction of the tangent vector of the curve, right? So dr points in the direction of the tangent vector. That means that dr is going to do what as you go around the curve, right? Dr is going to point around the curve. Right? And so thus, if f dot dr is going to give you a large value when f and dr are in the same direction, and dr points around the curve, then you're going to get a large result from this integral when f points around the curve. Okay, so if f points around the curve, what would we say about the motion of f, around the curve? We would say that if f is pointing around the curve, then there's a lot of circulation in f. That f has this whirlpool, circulation, rotation type behavior, right? So if these vectors are the dr vectors, and the result of our integral is going to be large when f is in the same direction as dr, then that's saying that then the f vectors, look very similar to this. In which case, if the f vectors, had this type of shape, we would say that in the vector field there is circulation or rotation around the exterior of the object. Okay, and so that's where we can go through and say that this integral of f dot dr over c, that's why we call it a circulation integral. It's because it measures circulation in the vector field. All right, it gives us a measurement of the circulation in the vector field. All right, so if the vector field has circulation tendencies, if it points around the curve like the red arrows, then you're going to get a large value from this, from this calculation. And if it doesn't, then you're going to get a really small calculation from this. Like, so just for hypothetical, if these red arrows, if they weren't rotating about this, if they just were, let's say, in a straight line, passing through, if they just pointed, down and to the right, as we go through our object, then then we would look at that visually and we'd say, oh, there's no rotation there. And if you calculated this f dot dr, then what you're going to find is you're going to find that you're going to end up getting 0 out of that. If you just think about going through and actually doing the calculations, if you had a red arrow, that's going to be, actually, I can draw in the red arrow. Actually, let me just show you this. This is kind of an important realization. Right, so if the red arrows pointed, down and to the right, just consistently, right? So you look at this and you'd say visually, well, there's clearly no rotation. So if there's no rotation, then we would expect that our circulation integral would give us 0. And that is the case if you had this type of behavior. So first of all, in some parts of it, like right here, you can see that the vectors are orthogonal. And so you'd get 0 there. And you can look at this and you'd be like, oh, wait, but hold on. Over in this part, we have the arrows pointing in the same direction. So don't I get a large positive value? Isn't that what you just said? You said that when they're parallel is when we get the largest positive value. Right, that's true. But since the dr vectors, since they are going around an object, that means that just like you have a part that's going to go in the same direction as the vector field vectors, the red arrows, you're going to have a part that goes in the opposite direction. And so you could say the dot product here is going to have the negative value of the dot product here, and they're going to end up canceling, right? And so because of that, you're going to have parts that give you 0, and you're going to have parts that are positive, and you have parts that are negative. It's all going to end up canceling out. So anyway, long story short, to get to the point, I'm already spending more time on this than I intended. This integral, what it does is it goes through and it calculates the degree of circulation in the vector field. All right, now let's move on to Green's theorem, which is why you're watching this video. What does Green's theorem say? It says that given f dot dr is a circulation, is a measure, that's what I want to do, is a measure of circulation around the exterior of D, right, of the object D, and given the curl of f dot k, right? So the curl of f dot k, if you recall the curl format, the curl of f dot k is going to be the k component of the curl, and that is that gives us a measure of rotation in the xy plane at a point. So this is going to be a measure of rotation at a point inside D. So what Green's theorem says is it says that these two quantities are equal. All right, so let's take a look at that and just think about it for a minute. So if this goes through and measures circulate, well, what is circulation? Circulation is rotation, right? So if this measures rotation around the exterior of D, and then this measures rotation at a point inside of D, right? So the double integral across D is going to go through and is going to go across the object D, the inside of the object D, calculating the rotation at each point. Then the notion that you have rotation around the exterior and rotation on the interior, and those end up being equal, it's not Looney Tunes. All right, so the notion that you could go through and calculate the rotation around the outer edge and then go through and calculate the rotation on the inside at all the points on the inside, and that those two quantities would end up being related is not insane. Okay, I mean, it actually does on the surface. It maybe makes some sense. Obviously, it requires some explanation, beyond just the statement. You wouldn't take it as a statement of fact, but you could go through and at least understand why we would say that rotation on the exterior of an object and rotation on the interior of an object, why those two things would end up being related. All right, so my plan was to clean up the picture, and instead I've erased it. So let's say, yes, so we could go through and we could calculate the rotation around the outer edge, and that's calculated by our circulation integral. And then we could go through and calculate the rotation at all the inside points, and that's calculated by our quantity curl f dot k, which gives us the rotation in the xy plane at a point, and then we could just compare those, and they end up being equal. All right, so that is what Green's theorem says. It says that the measure of rotation around the exterior and the measure of the rotation on the interior are equal. Okay. Now, again, that's maybe if you just think about it, you could be like, okay, yeah, I guess I could see that. I guess that's doable. But you should go through and maybe give it more than just a passing thought before you just accepted it as a law. All right, so let's go through and do that. Let's spend a few more minutes looking into this to see if we can go through and really prove this to ourselves that that's true. All right, so let's start off. I'm going to draw another picture. I'm going to draw the picture again. All right, so the idea is we've got our region D, and it's surrounded by C, and it's oriented counterclockwise. Right, and what I want to do is I want to go through and draw a square inside it, or not a square, a rectangle inside of it. And I want to go through and I want to find the rotation on that little square. Sorry, rectangle. Square, rectangle, it's all the same. All right, so I want to take that little picture there, and I just want to go off to the side and I want to blow it up. All right, so let's do that. Let's draw a big version of it and see if we can go through and calculate the rotation on that little piece. And then, just like every single time ever that we've gone through and worked with integrals, if we sum up a bunch of pieces, then those could end up adding up to a whole. So could we go through and sum up a bunch of these little rotations and end up getting the rotation around the outside, the whole rotation? If we could, then that would be a good explanation for why Green's theorem is true. That would essentially prove Green's theorem. So that's going to be the idea, is to start off by just looking at one little piece and then see if we add up a bunch of those, if we could end up getting essentially the sum around the big piece. All right, so let's go through and blow this up. All right, so this is a rectangle. We're going to say that this point here is x sub I, y sub j, right? This is not unusual. This is typically what we do. We go through and label things with x's sub i's, and with subscripts. If this side, what we're going to say is this is x sub I, but then you've added a change in x. And we're going to say that this side here is we've take change in x, and then from y we've added a change in y. And then finally this point here would be here, but we've added the change in y to the y coordinate. Okay. So a few things, right? So first of all, what we're going to say is we're going to say that this rectangle is really small. It is so small that we're going to say that the rotation around the exterior is constant on the sides, so that the rotation calculation that we do here, the rotation calculation we do here, 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 all the way across the side. We're going to say that the rotation calculation all the way across the one side here is going to be the same. And then we're going to say the same thing for this side, this side, this side. All right. So just and we're going to compartmentalize. We're going to say that this side is the same just for this side, because you don't want to go through and say, well, if the rotation is the same on this side, then that's going to say it's the same on this side and this side. That you no, one at a time. This side's all the same. 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 Okay. All right. So let me clean that up. That's the one critical piece here is we're saying that the rotation across the sides is the same. All right. So we're going to look at these one at a time, and that's the key to doing it. Is you have to just look at one and then set it aside, and then look at another independently. All right. So what we want to do is we want to find the rotation around the exterior here. To go through and do that, we're going to look at one piece at a time. We'll start with this piece. All right. So we want to know the rotation. How much rotation of the vector field points from here to here. That's what we want to know. So how much? Okay, so to go through and calculate that, we start off with f of x sub I comma y sub j. So we're going to use this point. And then what we can do is we can go through and we can take the dot product of I, right? If you took the dot product of I with f, what happens? You just get the x component from f. And that's what we want. We just want the part that's pointing in the x direction. Okay, and then I'm going to add a second thing here, and that's change in x. So we're going to take into account how long this piece is. So by dot producting with I, we're just getting the part of f that's just in the x direction. We're finding out to what degree the vector field here points to the right. And that's accomplished by just dotting with I. Okay, right? So if you've got a vector field and you go through, if you've got a vector and you've got a vector and you go through and you just dot with I, then you're just going to get the x component from the vector. And that's going to be the part of x that points in the x direction, the part of the vector that points in the x direction. All right. Now, if we actually did this calculation, what would we get? Well, if you go back, what is f? F is pi plus qj. So if you go through and you just dot this with I, you're just going to get p. So we're going to get p change in x. Whoops, I forgot something very important here, and that is p at the point here. X sub I, y sub j, change in x. Okay, and so that's the calculation of the amount of the amount of f that points to the right here. So that's kind of like, if you think of it like flow, how much is f flowing to the right? That's going to be this calculation. All right, now we're going to go through and do another calculation. I'm going to do the top part next. So the top part, that's for if we're thinking about rotating, and we want the rotation around our little rectangle to match with our rotation around the big object. So the rotation here has got to be counterclockwise. So if here we're rotating to the right, here we're going to be rotating to the left. Okay. Now there's a method behind this, which you'll see in the end. But what I'm going to do is I'm going to pick whichever side, because the rotation is constant across the side. I'm going to pick whichever side is more useful for doing a calculation in the future. And the side that's going to be more useful is going to be this side. So this is the side that we want. So we're going to go through and say that x sub I, y sub j dotted with. Now, this time instead of I, right, I would be the amount of here that's rotating that's going to the right. We want this going to the left. So we're going to do negative I. And we still have change in x is still the length of this piece. And if you go through and do the calculation here, you're going to get negative p. And then we're going to get, oh, whoops. We said we were selecting this point here. And then I plugged in the wrong stuff. All right. And so we're going to get x sub I comma y sub j plus change in y, change in x. All right, so that's the right side here. That's this calculation, and that's the left side here. And for this part, we use this point here, and for this part, we use this point here. So again, that's okay because we said that across the entire top, the rotation is constant. So the rotation calculation here and the rotation calculation here are, well, they're approximately equal. We're eventually going to take the limit as the number of these rectangles goes to infinity, and they will be exactly equal when we do that. All right, so those are those two calculations, and then we need two more. So we need this guy. So that's going to be x sub I plus change in x comma y sub j. So we're using this point for that guy, and then we're dotting with, so this direction is j, and then change in y. And if you take f and you dot it with j, then you're not going to get p, you're going to get q. So we're going to get q at x sub I plus change in x comma y sub j, change in y. And then we've got one more here, f. And then for this one, so now we're doing the downside, and then the calculation that's more useful to is going to be using this bottom one. So we're going to have x sub I, y sub j dotted with negative j, change in y, and we're going to get negative q, x sub I, y sub j, change in y. All right, and so if this calculation here comes from this guy, this calculation here comes from this one, this calculation here comes from that one, and this calculation is that one, then the amount of rotation is just going to be adding all those up. All right, so we're just going to add all them up. When we add them up, I'm not going to add up the left-hand side because that's not actually that useful. We're going to add up the right-hand sides here. All right, so when we add those up, what are we going to get? We're going to get p of x sub I, y sub j, change in x, minus p of x sub I, y sub j, plus change in y, change in x, plus q x sub I plus change in x, y sub j, change in y, minus q x sub I, y sub j, change in y. All right, and now what we can do here is we can go through and we can, I'm going to factor out the change in x from these top two. I'm also going to change the order and pull out the negative here. So we're going to have negative, and then we'll have p x sub I, y sub j plus change in y minus p x sub I, y sub j all times change in x. And then here I'm going to not going to change the order this time. We're going to leave it x sub I plus change in x, y sub j, minus q of x sub I, y sub j, change in y. Okay. So what have we got here? If you look at this, this looks kind of, I mean, it's got components, it's got parts of our definition of a partial derivative, right? If you go back and look at the partial derivative definition, this looks like the partial derivative, part of the partial derivative in the y direction. This looks like part of the partial derivative in the x direction. So what we can do is we can go through and say p of x sub I, y sub j plus change in y minus p of x sub I, y sub j divided by change in y, right, is going to be approximately equal to the partial derivative with respect to y partial derivative of p with respect to y. And this will be exactly equal if we go ahead and take a limit as change in y goes to 0, which we will do if when we go through and add up our summation, or when we add up pardon me, when we go through and take these little rectangles and cover the entire object with them and make them infinitesimally small. When we make them infinitesimally small, you take the limit as change in y goes to 0. And so when that happens, these two become equal. But for now, we're just going to say they're approximately equal. And then we can go through and say, if that's true, you can take the change in y here and move it over to the other side, and we'll get p of x sub I, y sub j plus change in y minus p of x sub I, y sub j, right, is approximately equal to the partial of p with respect to y times change in y. Okay. And so what that allows us to do is just to plug that in here. We're going to get negative, and then this is going to be partial of p with respect to y, change in y, change in x. So I've substituted for this with the calculation we just did. And then you could do a similar thing with this piece here. This is going to be the partial of q with respect to x times change in y. Oh, hold on. Times change in x. And then times change in y. Change in y is the one that's outside. And then we can go through and simplify this. You can, pull out the change in y here, pull out the change in x there, and we could rewrite this. This is the partial of q with respect to x minus the partial of p with respect to y times change in x, change in y, or vice versa. Or if you go through and just recall, what is that? That's the k component from the curl calculation. So that's also the curl of f dotted with k. By dotting with k, we're pulling out the k component from the curl. And so this is the curl of f dot k, change in x, change in y. All right. And so we could go through and see by that exercise that the rotation around a little box is going to end up equaling this quantity or this quantity, right? So what does that mean? That means if we went through and moved that little box all around the object, right? We went through and took the limit as m and n went to infinity for our double integral here, I equals 1 to n, j equals 1 to m, curl of f dot k, change in x, change in y, that we would end up getting the double integral d curl of f dot k dA. All right, so what I've done there is I've gone through and taken my single rectangular box, and I just said, okay, well, I can take that and I can vary it across this entire D object. And if I do that, since the calculation it ends up turning into this curl of f dot k, then when I do that, I'm going to end up with a double integral of curl of f dot k dA. All right, so what we've done there is by going through and taking our little box and moving it around, we've gotten the right-hand side of Green's theorem. Okay, so now the question is, what about the left-hand side? All right, what about the left-hand side? Well, take a look at this. This is cool. At least it's cool for math. Whoop, hold on, that was supposed to be a line. All right, let's see if I can do a halfway decent job here. I'm gonna draw an object that's kind of strangely shaped, but there's a reason for that. All right. Suppose we had an object like this. Now it doesn't have, it could be shaped like any shape, but I'm intentionally trying to draw a particular shape here. All right, now suppose we went through and we took our rectangular box that we found that we represented here. Suppose we went through and put rectangular boxes actually into a shape, right? What would happen if we went through and added these up? Actually, they're supposed to line up. Let me try that. Let me try that part again. All right, it's not going to be perfect, but the point is to illustrate something anyway. If you actually were filling these with rectangular boxes, then they would be a lot smaller than this, and you'd end up using an infinite number of them. So we're just illustrating something with this. All right, so we go through, we fill this with these rectangular boxes. Like that. All right. Now, what happens if we actually go through and add these up? All right, so we want to go through and actually do this calculation. So we know that in this calculation, we're taking this side, the right-hand side, and then we're adding this, we're finding this calculation, and then we're taking this piece, and then we're finding that and adding it, then we're finding this piece, and then we're adding that, and we're finding this piece, and we're adding that. So now, instead of thinking about doing all of it at once, which is what we did in doing this calc in determining that the rotation ends up being this, instead we're going to think about doing them one at a time. All right, so we go through and we find this amount, this amount, this amount, this amount. All right, so we've got the rotation for that guy. Okay, and then after that we go through and let's do this one next to it. So we go through and we find this amount, this amount, this amount, and this amount. Notice this spot where we have the arrows pointing opposite directions. One of those is going to be rotation up. The other one's going to be rotation down. Those are going to have the same value, but one's going to be positive and one's going to be negative. What happens if we take a positive and we add a negative to it? The two cancel. So when we do these two boxes next to each other, it cancels that piece. All right. So now what we've got, when we took these two boxes and added them, we have the rotation here. All right, now let's go through and add this guy to it. So we go through and we add this, add this, add this, add this. Oh, look, we've got another spot where we've got cancellation, cancels that piece. All right, and so now we've got rotation around this piece, and it looks like that. All right, so now let's add this piece. So we've got there, 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 there. Oh, oops, those cancel. How about the next one? There, 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 there. And then you can go through and you can just kind of draw in all of these, right? What's going to happen? You could kind of figure this out for yourself, pretty quickly. If we go through and label all of these, what are the spots that have the double arrows? Where are the double arrows? Here, 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 and here. Oh, and look at what happened. We ended up by going through and taking our little rectangle calculation, and by moving it around the exterior, we ended up canceling everything except for the exterior. All of the interior canceled. All right, so symbolically, what would that look like? Well, so we still have our calculation of all of those sums. It's still this. So we would still have that as our starting point. So we still have, all right, well, we're going through and doing the limit as m and n go to infinity. And we've got our double summation, I equals 1 to n, j equals 1 to m, curl of f dot k, times change in x change in y. But now we're not going to say that this equals this. Instead, what we're going to say that it ends up equaling the sum of the exterior I'm just going to put calculations here because we need to figure out what those calculations are. The sum of the exterior calculations where each one of the red arrows is a calculation. So what are these calculations? We need to add those up. All right. So what are we calculating with those little arrows that are on the exterior? All right. Well, let's pick an example. All right. So we've got this piece is one of them, right? This is one of those. That piece there, that's going to represent the calculation here, 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 and here. So that's 3 of them. And then we've got, all the rest are in there too. But we're just going to pick on this one, right? On the one that's moving to the right. And then we're just going to say, okay, well, the ones that are moving up to the left and down, those are the others, and you could just kind of extrapolate. All right, so we've got this guy here. Let's just transcribe that over. So what is that? That was f of x sub I, y sub j, dotted with I change in x. All right, so what is that? Well, off to the side here, let me show you something. So what do we know about x? If we go over to our picture here, we've got a bunch of x's. Where did those x's come from? What do we have any definition for those x's? If you go further back, all the way back to the very beginning, we said that x was part of going through and defining the curve, and that it's defined in terms of t using our parametric equations. So watch this. Something cool you can do. You can go through and you can say, all right, well, x equals x of t. All right. And then that means that, so we know that x prime of t, right, is approximately equal, there's that approximate equal again, change in x over change in t, right? This is going all the way back to the very, very beginning of calculus, where we're going through, and this is like the tangent line derivative. This is like the secant line derivative. These are approximately equal. If you take the limit as change in t goes to 0, then these become exactly equal, right? So that's our definition of the derivative if you throw a limit as change in t goes to 0. All right, but we're not going to do that. So what we're going to say is that we can use this definition to move the change in t over, and you'll get that change in x is approximately equal to x prime of t change in t. Okay. Also, what else do we know? We know that r of t equals x of ti plus y of tj. What is that? That's going back all the way back to the very beginning. If you take your parametric equations, you could combine them to form a vector function. All right, and so that's what we've done here. I've combined them to form our vector function. However, notice that in these pictures, our arrow is just going to the right. All right, so we don't have any vertical component. It's just the horizontal component. So if you go through and you zoom in so that you only have a horizontal, so that the interval is only horizontal, then what you're going to end up getting out of your vector function is just this component. How can you go through and, what would that look like? So that means you're going to have r of t equals x of ti. Okay. And now next, if this is true, both sides are in terms of t. So we could go through and differentiate both sides, and we'll get r prime of t equals x prime of t. Okay. And then one more thing here, if you go through at this point and you just multiply both sides by change in t, you'll get that r prime of t change in t equals x prime of t change in t. Okay. All right, and now let's go back over to this piece here. So this is the calculation for going through and finding these parts that are pointing to the right, the parts of the exterior that are pointing to the right. If we go through and write this out, we could change this over to t. This would be x of t sub I, y of t sub I, y of t sub I. So I'm taking my parametric equation and I'm actually plugging it in here. Then this is going to be dotted with I, right? And then change in x, if you go through and plug in t, we said that change in x equals, or is approximately equal to x prime of t change in t. Is x prime of t change in t, right? And then what is x prime of t change in t? Okay, we said that that is r prime of t change in t. Okay, and if we only have the horizontal, we can go through, and if this is only the horizontal, then this whole thing becomes r prime of t change in t. Okay, so that's taking this piece right here. So if we zoom in so that this is just horizontal, then r of t equals x of ti, right? And then we can go through and say that we can go through and oops, I forgot the I here. So there's supposed to be an I there. That's why I was getting a little confused there. If you throw an I in there, then this r prime of t change in t equals x prime of t change in ti, as long as you've got, as long as it's just horizontal, right? So as long as you have you zoom in so that you just have a horizontal piece, which is what we have here. We're just looking at the horizontal calculations and we're not taking into account any of the vertical parts. Okay, now if you look at that, what is that? All right, if you look closely at that, if we just kind of, shorthand, that's f dot, that's our f dot dr. Okay, and so what we can do now is we can go through and say that this, this calculation, we've got the limit as m and n go to infinity of summation I equals 1 to m, j equals 1 to n. I think I got the I and the j the reverse there, but it doesn't matter. Curl of f dot k, change in x, change in y, we can say that this equals the limit as, I don't know, we should probably use a different letter. O goes to infinity of the summation k equals 1 to O of this, right? This guy here. So f of x of t sub I, y of t sub I, r prime of t sub I change in t. All right, sorry, there's a little strange shape there. My recording software has a box that's right in the way there. Anyway, and so this side becomes our double summation of d curl of f dot k dA, and then this side becomes the single integral f dot dr over c over closed curve. And so that's the long form, which again took a little bit longer than I expected to go through and explain all of that. But the idea is this is really important in terms of understanding, because this is going to be kind of the same argument we use to go through and explain why Stokes' theorem and the divergence theorem is true as well. And that is that if you go through and you're trying to show that Green's theorem is true, the way that you show it's true is by showing that the rotation calculations on the interior, you get all that cancellation when you do the rotation this rotation calculation on the interior, you get all that cancellation. And when all the interior parts cancel, you end up getting just the rotation that's on the exterior. And so that's a critical piece of understanding Green's theorem, is that cancellation process. And so that's why I wanted to show it to you, right? So again, if you litter all the inside with boxes, then the inside all cancels and you just get the exterior. Anyway, so that's why Green's theorem is true, right? So here are calculations on the interior, and then all the interior pieces cancel and we get our calculations on the exterior. All right, examples. Let's see some examples. All right, so suppose you're asked to go through and use Green's theorem to evaluate the line integral C over curve C, x squared plus y squared dx plus x squared minus y squared dy. And you're told that C is the triangle zero, zero, 2, 1, 0, 1. Okay, so it says use Green's theorem to evaluate the line integral, and it gives you what C is. All right, so one of the key things to understanding how to use Green's theorem is if they tell you to use Green's theorem to evaluate a line integral, they're not saying calculate the line integral directly. If they want you to calculate the line integral directly, you know, like using the information from previous sections that we've covered in, you know, in vector calculus, they would say go through and they would just say evaluate the line integral. So what they don't want you to do is they don't want you to go through and, you know, find the parameterization for the triangle and then plug it in and evaluate it directly. Now they're saying use Green's theorem. How do you use Green's theorem? How do you use a theorem? Well, what does Green's theorem say? It says that a line integral is equal to a double integral. So if they say use Green's theorem to evaluate a line integral, they're not saying to just evaluate the line integral. They're saying to evaluate the double integral. So you want to switch over to the double integral and replace this with the double integral. That would be using Green's theorem to evaluate this line integral. All right, so I hope that makes sense. It's a little convoluted there, but that's the way that the instructions typically are in problem sets when it comes to going through and practicing using Green's theorem, is they'll tell you to use Green's theorem on a line integral, and what they don't mean is to calculate the line integral directly. They mean to change over to the double integral, calculate the double integral, and by calculating the double integral, you will have found the line integral instead. And you'll have used Green's theorem as part of that process. All right, so this is the second format for Green's theorem. You could think of this as P, this is Q. And so the second format for Green's theorem says you take the partial of Q with respect to, actually, let me just write it here. Partial of Q with respect to X minus the partial of P with respect to Y. You do that over your object. All right, so let's go ahead and do those calculations. The partial of Q with respect to X, if you differentiate this with respect to X, you get 2X. And if you differentiate this with respect to Y, you get 2Y. dA over our object D. Now, what is our object D? To figure out what the object is, you know, with these types of problems, you need to look at C. D is what's inside of C, right? C is the curve surrounding D. So you can go through and just sketch yourself a little picture to figure out what D looks like. So you've got 0, 0, you've got 2, 1, and you've got 0, 1. So we've got a triangle. All right, and so to go through and evaluate this, we need to go through and figure out the bounds for this triangle. All right, well, this is, you could use type 1 or type 2 here. It doesn't matter. Since it doesn't matter, I typically tell students to try and do, type 1 is a top to bottom calculation. So you tell people to do top to bottom if they can. So top to bottom is dy, then dx, right? So dy, because you're doing y distances first, and then you're moving that in the x direction second. All right, and so what are those y distances? Well, we need to know the equation for this in terms of y. Right? How could we do that? Well, it's just a line through the origin that has a slope, right? So what's the slope? You go up 1 over 2. So that's 1/2 x, and then since the line goes through the origin, the y-intercept is 0. So we're going to have 1/2 x for the bottom, and then for the top, that top it has a y value of 1, so that's y equals 1. So we have 1, and then we want to do that from x being 0 to x being 2. All right, so let's go ahead and just quickly evaluate that. It's the antiderivative of this with respect to y. We're going to get 2xy minus y squared. Evaluated 1/2 x to 1. We get 0 to 2. Plug in 1 for y. We're going to get 2x minus 1 minus, plug in 1/2 x for y. 1/2 x times 2, that's going to be x. We're going to have x squared minus, and then plug in 1/2, we're going to get 1/4 x squared dx. And then here, this is integral 0 to 2. What do we got? This is 4/4 x squared minus 1/4 x squared. So we get 3/4 x squared. So we got 2x minus 1 minus 3/4 x squared. And that's dx. And so we can go through and find the antiderivative. The antiderivative of 2x is x squared minus x. And what do we got here? This is going to be x cubed over 3. The 3's are going to cancel. So we're going to x cubed over 4. Evaluated 0 to 2. It's going to be 4 minus 2 minus 2. And so it looks like we get 0. Okay. And so that would be a perfect example of going through and using Green's theorem to evaluate a line integral. Again, we did not end up evaluating a line integral. We ended up evaluating a double integral, but that's the point of Green's theorem, is that a single integral equals a double integral. So if you're asked to use Green's theorem to evaluate a single integral, do not evaluate the single integral, evaluate the double integral. And hypothetically, if you're ever asked to go through and use Green's theorem to evaluate a double integral, don't evaluate the double integral, because if they wanted to evaluate the double integral, they would just say evaluate the double integral. If they say use Green's theorem to evaluate the double integral, then they mean for you to evaluate the single integral. That's how you would use the theorem to actually do the evaluation, would be by using the other side of the theorem. Okay, let's go through and do another one here. So again, you're told to use Green's theorem. Big surprise there, told to use Green's theorem in the section on Green's theorem to evaluate f dot dr over c, where f equals square root of x squared minus 1 arctan x. And C is the triangle from 0, 0 to 1, 1 to 0, 1 to 0, 0. Okay, so this time we have the second form of Green's theorem. And so, or the first form, I guess, whichever, the form with f. This time we've got the form with f. And so the form with f says that we get curl of f dot k dA. And so again, we're asked to use Green's theorem to evaluate the line integral. That does not mean to evaluate the line integral. It means to use the double integral to do so. So to use the double integral, we need to have the curl of f. So let's go off to the side. Curl of f. All right, now one of the things you might think, oh, well, f only has 2 components. How could we use the curl when the curl has 3? Just put in 0 for the missing component. All right, so in this case, a 2-dimensional vector field doesn't have any z components, so it has 0 for z. So we could use partial with respect to x, partial with respect to y, partial with respect to z, and then we're going to have square root x squared minus 1 tan inverse of x 0. So we're going to get I times 0 minus 0 minus j 0 minus 0 plus k. And then the derivative of tan inverse is going to be the square root of, well, not square root, what am I saying? Looking at this, thinking ahead. It's going to be 1 over 1 plus x squared. And then minus the derivative of this with respect to y. There's no y's here, so this is all treated like a constant, and the derivative of a constant is 0. Okay, so we've got our curl of f. And if we go through and pop that in, right? So if we've got 1 over 1 plus x squared times k, right? And that's a regular times. Let's just actually get rid of that time. Let's just say that's 1 over 1 plus x squared k. And then you dot it with k, right? This is another k here. What that's doing is it's saying take the k component from these 3. And that's going to be just the third one. All right. And so k component dotted with k is just going to be that the component without the k, just the 1 over 1 plus x squared. All right, and so from that, we're going to get 1 over 1 plus x squared dA over d. All right, so what does d look like? We can figure that out. Drawing ourselves a picture here. We've got 0, 0, 1, 1, 0, 1, 0, 0. So here to here to here to here. All right, so it's just this triangle. Okay, so that's our D. And again, type 1 or type 2, whichever one you like. I tell students, if you can, to go through and do it vertically. All right, and so vertically, we need to know the equation for the bottom object here. It goes through 0, 0, and 1, 1. That's y equals x. The top, that's y equals 1. And so now we can go through and set up our double integral on the next page. So we're going to have 1 over 1 plus x squared. We're going to do dy, then dx. For dy, what did we say we're going to have? It goes from the bottom to the top. So that's from x to 1. So we have x to 1. And then you do that from, I believe, 0 to 1, right? 0 to 1. Yep. So here's the x value, 0, x value, 1. All right. So we want to do that from 0 to 1. And from there, it's just all plug and chug here, just old school differentiation. So the antiderivative of 1 over 1 plus x squared with respect to y is going to be 1 over 1 plus x squared times y, evaluate x to 1 dx. And so we're going to have 0 to 1, plug in 1, you get 1 over 1 plus x squared, minus plug in x, you get x over 1 plus x squared. All of that dx. And then here we could just go through the antiderivative of 1 over 1 plus x squared is going to be, well, we just did it, right? It's going to be arctan of x. And then the antiderivative of this, this is a u substitution where we've got the top is the derivative of the bottom. That's a classic like natural log problem. If you go through, one of the things you can do with these, you can just kind of guess and check. So let's say we guessed that this was our antiderivative. Then if you check it, you could check it by differentiating this. If you differentiate this, you get 1 over 1 plus x squared times 2x. Are these the same? Look at them. No, but they're close. They're just off by a 2. So if you put in a 1/2 here, then that will make it so that they're the same. So you can do little, little shenanigans like that when you get a lot of experience with integration. And then, so once you've gone through and you found your antiderivative, then you just plug in 1. So we get arctangent of 1 minus 1/2 natural log of 1 plus 1 squared. All right, minus arctangent of 0 minus 1/2 natural log of 1 plus 0 squared. All right, and so what are those going to be? So what angle do we plug into tangent to get 1? That would be pi over 4. 1 squared is 1, 1 plus 1 is 2. So we're going to get minus 1/2 natural log 2. And then what angle gives a tangent? Tangent of what angle is 0? And that's going to be 0. And then 0 squared is 0 plus 1 is 1. Natural log of 1 is 0. And so this is our answer. And sometimes you might see people just thinking they're being really clever. They might take the 1/2 and bring it inside here, and they get 2 to the 1/2 instead of having that 1/2 in front of the natural log. All right, and so there's a second example of going through and using Green's theorem. And I know I've repeated myself probably one time too many already, but again, when you're asked to go through and use Green's theorem to evaluate a line integral, you should not be evaluating the line integral, you should be evaluating the double integral. And that's what I did on both of the example problems. Okay. All right, so that's Green's theorem in all of its glory. I hope you enjoyed the explanation here for why Green's theorem is true. It's not a common explanation that I've seen very many places. I found it in a calculus textbook, and it really opened my eyes to why Green's theorem really does make sense. Without it, if you don't have it, then you're kind of just taking Green's theorem on faith. And that's my experience has been that, when talking to other calculus instructors, or even when I took calculus myself, that was the case. It was just kind of like you get to Green's theorem and you're just like, it's just true. Just trust us. Just trust us. And so I hope that this explanation at least gave you something, even though there's a little hand wavy in here saying, hey, well, the sides are small enough that the endpoints are equal. It gets a little hand wavy in there, but it's at least you got something to hang your hat on, where you can kind of feel like you've got some understanding of why Green's theorem is true. All right, well, thank you for watching, and I will see you next time.